Hello. In today's video, we're going to explore some fundamental principles of statics, a branch of physics that deals with forces and their effect on stationary objects. By the end of this lesson, you will be able to first, understand how to combine forces using the law of parallel forces and the theorem of a force system. Second, analyze and solve problems related to an object in equilibrium. Third, apply geometric methods, like the force triangle, and algebraic methods like Lamy's theorem to solve equilibrium problems involving three forces. And fourth, tackle more complex problems, like those involving multiple forces acting on a hexagonal object. These concepts are not just for academics, they are essential for engineers, architects, and anyone who needs to understand the stability of structures. Let's begin. Let's start with combining forces. You can think of a force as a vector. It has both a magnitude and a direction. What do we do if we have two forces acting at the same point? First, we have the law of parallel forces. Imagine a plank. A heavy person stands on it at one point, and a lighter person stands at another point. Together, they exert a total downward force. So we have two forces, F1 and F2, that are parallel to each other. The law of parallel forces states that the magnitude of their resultant, R, is simply their sum. R equals F1 plus F2. Visually, it looks like this. If two forces, F1 and F2, are acting in the same direction, their resultant is a single larger force R, and its magnitude is just the sum of the magnitudes of the two forces. This law is very intuitive for forces acting along the same line or in parallel directions. It's simply saying that their effects add up. What if the forces aren't parallel? This leads us to a more general rule for combining forces. We call this the theorem of a force system. The theorem states that any system of concurrent forces can be reduced to a single resultant force. Concurrent forces are simply forces that all pass through a single point. The most straightforward way to find this single resultant force is using the parallelogram law. Let's say we have two forces, F1 and F2, acting at a point. We can form a parallelogram with F1 and F2 as adjacent sides. The diagonal of the parallelogram, starting from the point where F1 and F2 originate, represents the resultant force, R. This resultant force has the same effect on the object as the two original forces combined. So, to recap, the theorem of a force system tells us that we can always simplify multiple concurrent forces into a single equivalent resultant force. A common way to find it is with the parallelogram law. Now, let's talk about the most common scenario we'll analyze in statics. That is, the equilibrium of an object. In physics, equilibrium means that all forces acting on an object are balanced. The object is either at rest or moving at a constant velocity. For statics, we are primarily concerned with objects that are at rest. The fundamental condition for equilibrium is that the net or total force acting on the object must be zero. Think of a book resting on a table. The force of gravity pulls it down, but the table pushes up with an equal and opposite force, called the normal force. These two forces cancel each other out, and the net force is zero, so the book remains at rest. Mathematically, we write this as the sum of all forces is equal to zero. This is a vector equation. To solve problems, we typically break the forces into their horizontal, or x, components, and their vertical, or y, components. The vector equation then becomes two separate scalar equations. The sum of the x components is zero, and the sum of the y components is zero. This gives us a powerful tool to analyze and solve for unknown forces in systems that are not moving. We break the problem into simpler, one-dimensional pieces. A very common situation in equilibrium problems involves only three forces. For this specific case, we have two elegant methods to find a solution. The first is the theorem of a force triangle. If an object is in equilibrium under the action of three concurrent forces, then those three forces can be represented in magnitude and direction by the three sides of a triangle, taken in order. Let's see what that means. If we have three forces, F1, F2, and F3, keeping an object in balance, we can draw them tail to head. Because the object is in equilibrium, the vector sum of these forces is zero. This means that if we add F3 to the head of F2, we must land exactly back at the tail of F1. The vectors must form a closed loop, a triangle. If they don't form a closed triangle, the object is not in equilibrium. This theorem is incredibly useful. We can use the geometry of the triangle, along with the law of sines and cosines, to solve for unknown force magnitudes or directions. It provides a visual and intuitive way to understand the balance of three forces. Now for an algebraic approach to the same problem of three concurrent forces in equilibrium. We can use Lami's theorem. This theorem provides a direct relationship between the magnitudes of three forces and the angles between them. It's often quicker to use than the method of components or the force triangle when you have three forces. Here is Lami's theorem. It states that if three forces, P, Q, and R, acting at a point are in equilibrium, then each force is proportional to the sine of the angle between the other two. Let's be very clear about the angles. Alpha is the angle between forces Q and R, beta is the angle between P and R, and gamma is the angle between P and Q. This means if you have the magnitudes of two forces and all the angles, you can easily find the third force. Or, if you know all the angles and one force, you can find the other two. Let's take a common example. A weight hanging from two ropes. We have a downward force from the weight, let's call it W, and two tension forces in the ropes, T1 and T2, pulling upwards. To use Lami's theorem, we first need to define our angles. Remember, we need the angles between the forces. The angle between T1 and W is 90 plus 60 degrees, which is 150. The angle between T2 and W is 90 plus 30 degrees, which is 120. The angle between T1 and T2 is 180 minus 30 minus 60, which is 90 degrees. Now we can apply the theorem. T1 over sine of 100 and 20 equals T2 over sine of 150 equals W over sine of 90. The weight W is mass times gravity, so 10 times 9.8 is 98 newtons. Sine of 90 is 1, so we have T1 over 0.866 equals T2 over 0.5 equals 98. We can now solve for the tensions. T1 equals 98 times 0.866, which is 84.87 newtons. And T2 equals 98 times 0.5, which is 49 newtons. Lami's theorem provides a very quick and efficient way to solve these kinds of problems. So far, we focused on two or three forces. What about more complex situations, like those involving many forces on an object? Let's tackle a classic problem to see how our principles apply. We will solve a problem on a regular hexagon A, B, C, D, E, F. The problem states that forces represented by the sides AB, AC, AD, AE, and AF act at the vertex A of a regular hexagon ABCDEF. We need to find their resultant. First, let's visualize the setup. We have a regular hexagon. The vertex A is where all the forces are applied. The forces are represented by the five vectors AB, AC, AD, AE, and AF. This seems complicated, but we can solve it by finding the components of each force along the x and y axes. Let's place A at the origin and let the force AB lie along the x-axis. A regular hexagon has internal angles of 120 degrees. Let's use trigonometry to find the components of each force, which we'll call P. Force AB is purely horizontal, so its components are P and 0. Force AC makes an angle of 30 degrees with the x-axis, so its components are P times cosine 30 and P times sine 30. Force AD is purely vertical, so its components are 0 and P. Force AE is at 150 degrees, so its components are P cosine 150 and P sine 150. Force AF is at 210 degrees, so its components are P cosine 210 and P sine 210. Now for a clever observation. Let's look at the x components. We have P plus P times root 3 over 2 plus 0 minus P times root 3 over 2 minus P times root 3 over 2. Notice that the components from AE and AF cancel out with the component from AC. They have the same magnitude but opposite signs. So, the total x component of the resultant is P minus P times root 3 over 2. Now for the y components. We have 0 plus P times 1/2 plus P times 1/2 minus P times 1/2. Again, we see a cancellation. The y component from AF cancels with one of the components from AE or AC. We are left with 0 plus P times 1/2. So the total y component of the resultant is P plus P times 1/2. We have found the components of the resultant force without tedious calculations thanks to the symmetry of the hexagon. Now we can find the magnitude and direction. The magnitude of the resultant r is the square root of the sum of the squares of its components. This gives us r equals p times the square root of 5 minus 2 root 3. The direction is the angle theta, which is the inverse tangent of ry over rx, which is approximately 67.9 degrees. So the 5 forces combine into a single force of that magnitude and direction. Let's summarize what we've learned today. We started by understanding how to combine forces. The law of parallel forces helps us add forces in the same direction, while the theorem of a force system provides a general method for concurrent forces using the parallelogram law. In statics, our main focus is equilibrium, the state where an object is at rest. The key condition for equilibrium is that the vector sum of all forces acting on the object must be 0, or in components, the sum of all x forces and all y forces must be 0. For the special and common case of 3 forces in equilibrium, we have 2 powerful tools. The force triangle is a geometric method, and Lami's theorem is an algebraic method that relates force magnitudes to the sines of the angles between them. Finally, we applied the method of components to solve a complex problem involving 5 forces on a hexagon. This demonstrates that by breaking down complex problems into their basic components, we can solve them systematically. The concepts we've covered today are foundational for much of engineering and physics. Understanding forces and equilibrium allows us to design safe bridges, stable buildings, and functional machines. Thank you for watching.